All right, so today we're going to take a look at polynomial theory and the end behavior of graphs. And we're basically going to cover two sections worth of material. And as far as polynomial theory is concerned, I believe this was in the 4.2 and 4.3 modules. But for polynomial theory, we have what are called zeros, and we have linear factors. Okay. Now a zero, okay, this is going to be written out in abstract terms. A zero can be written in the form of C, right? And C can just be any number. Can be a constant, can be a fraction, can be a decimal, can be any real number. A linear factor is written in the form x minus C. So we can convert zeros to linear factors, and then vice versa. We can convert linear factor to zeros. Now, we talked about zeros, and a physical representation of a zero is an x-intercept. Okay, so what we're going to basically be doing in this section is taking a look at some graphs, and based on those graphs, we're going to try to write out the equations. All right, but first let's take a look at some examples. All right, we're going to, okay, and here's just an example. So we're asked to write the function of the following graph. All right. All right, so this is a very rough sketch of a graph. So here we have an x and a y coordinate. Here we have -2. Here we have +2. I'm not going to be all elaborate on the graph. And I'm just going to draw a U-shaped graph. And it's supposed to pass between the points -2 and +2. All right, and we're asked to simply write an equation for the following graph. Right, so the only thing we're basically given is we know the fact that it's a quadratic equation, right, because the graph forms a U shape. And we're also given the two zeros. We're given a zero of -2, and we're given a zero of +2. Right, so we're going to convert the zeros to linear factors. So notice that the linear factors are in the form x minus your zero. So in order to convert -2 to a zero, I'm just going to use the form. I'm going to put in x minus the zero, which is a -2. That double negative makes a positive, so -2 as a zero equals x plus 2 as a linear factor. Now I want to convert +2 to a linear factor. So I'm simply going to go back to the model form. The model form of a linear factor states that it's x minus the constant, or x minus c. In this case, the constant is 2. So we have our linear factor x minus 2. All right, so we've taken the zeros and we've converted the zeros to linear factors. Now, how do we form the equation? Well, to form the equation, we're simply going to take those linear factors and we're going to multiply them. Right, we're going to use the FOIL method. Right, so we've converted the zeros to linear factors, and now we're going to multiply the linear factors to form an equation. So I'm just going to use the FOIL method. So x times x is x squared. I can multiply my outermost terms. -2 times x is -2x. I can multiply my innermost terms. 2 times x is 2x. I can multiply my last terms. A positive times a negative is a negative. 2 times 2 is 4. The 2x is canceled, so the equation we have is y is equal to x squared minus 4. All right. So now I'm going to give you a problem to try. So here again, we're going to write the equation for the following. All right, so we have -1, we have 0, and a +1. So this graph hits here. Okay, so it hits at all right, so here we have the graph, right? It hits the x-axis at -1, 0, and +1. Right. I'm going to give you a few minutes, and I would like for you to write the equation for the graph, and then we'll come back and we'll take a look at the solution together. All right, let's take a look at the solution. So first we have the zeros, which are -1, 0, and +1. We're going to convert those zeros to linear factors. So x minus 1 as a linear factor is x plus 1. 0 as a linear factor is simply x, right? Because you take x minus the 0, so you have x minus 0, which is x. And then a linear factor for +1 is x minus 1. All right, so notice I'm putting those linear factors in a set of parentheses. So now we're going to write out the equation. So I'm going to write out x times x plus 1 times x minus 1. And I'm simply going to multiply. So the first thing I'm going to do is distribute x within the first set of parentheses. So x times x is x squared. X times 1 is x. I'm going to bring down my next set of parentheses, x minus 1. And now I'm going to simply use a FOIL method. So I'm going to multiply my first term. So x squared times x is x to the third. Multiply the outermost terms. X squared times -1 is negative x squared. Multiply the innermost terms. X times x is positive x squared. And we'll multiply the last term. So x times -1 is negative x. The x squared cancels, so we have the equation as x cubed minus x, right, as our equation. So one thing, notice that this graph forms that S shape we talked about, right, which alludes to the fact that it should be a cubic equation. Okay. Now next we're going to talk about multiplicity and zeros, sort of quick. So just to kind of write out in a quick example. All right, so here's just an example. And normally the questions are in the homework like this. You'll see something that says y is equal to, let's say, x, and then x plus 1 squared, and then x minus 3 cubed. All right, and then we'll have a chart, and it wants the zeros and the multiplicity. Now we talked about the zeros already, right? We could take each one of these linear factors, but notice now a linear factor, if we take a look at these three factors, we have x, we have x plus 1, right? And x plus 1 is a factor that's encapsulated in a set of parentheses. It has an exponent of 2. We have another linear factor, x minus 3. It's encapsulated in a set of parentheses with an exponent of 3. So to determine the multiplicity, we simply reverse the process. We take, and I'm saying linear factors, but some of these things aren't linear, right? A linear factor actually has an exponent of 1. So if I look at this first factor, x, right? And from what we did earlier, I'm going to kind of go back up. If x is a linear factor, then in a zero form is written as simply 0, right? So I'm given a linear factor x, and the linear factor x as a 0 is 0. So one of my zeros are 0. Now for the multiplicity, you simply look for the exponent that that factor carries. So for example, that x is raised to the first power, so that 0 has a multiplicity of 1. If we take a look at the next factor, it's x plus 1 quantity squared. But if we look inside of the parentheses, we see a linear factor of x plus 1. Right? So in order to find the 0 given a linear factor, you simply reverse the process. I'll take the linear factor, x plus 1. I'll simply set it equal to 0 and solve. So our next 0 is a negative 1. So now in order to determine the multiplicity, we're going to look at the exponent that that linear factor carries. So the factor x plus 1, which is a 0 of negative 1, carries an exponent of 2. So it has a multiplicity of 2. And if we look at the third factor, x minus 3, x minus 3 as a 0 would be positive 3. And to determine the multiplicity, we simply look at the exponent it carries, which is 3. All right, so we have our zeros and our multiplicity. Okay, now the next and last thing I want to talk about today is something called end behavior of graphs. Oh, I'm sorry. I guess I should have kept up this screen. Okay, I'm going to go back to our main page. I added something called documents. Okay, this very last link at the bottom. I'm simply going to click on that. And I added this document called end behavior. Okay, so I'm just going to pull this up. I'm actually going to download this to the computer and pull it up. All right, so this is the document that I'm using. It's in the document section of our Blackboard homepage, okay, as a reference. All right, so notice this is from a different book, so the information might be a little bit different. Okay, but this is what we want. We want to talk about what's called the end behavior of a graph. All right, so this might look a little bit confusing, but I want to concentrate on the pictures that are at the top, okay? And I guess I should explain some of these terms. You probably have heard me say these things. Okay, so I'm going to just go back one slide. Okay, now this wasn't actually a part of your textbook, but it is pertinent to this course. All right, and we have the definition of a polynomial function, and it's written out in this form: P of x is equal to, and if you look at that very first term, it's a sub n. And if you look at the bullet points below, a sub n is called the leading coefficient. Right? A coefficient is just the number part of your term. The leading coefficient would be the number part of the variable with the largest exponent. A sub n times x to the nth power. All right, so I'm still looking at that polynomial function form. And it's that very first term, a sub n times x raised to the power of n. That's called the dominating term. All right, so the dominating term is the term whose variable has the largest power. That dominating term also has a leading coefficient. And then we have plus a sub n minus 1 times x to the n minus 1 dot 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 a sub 1x plus a sub 0, where a sub 0 is called the constant term on the end. All right, so when you hear me say leading coefficient and dominating term, I'm talking about the term in the polynomial that has the largest exponent, right? So that's what we're going to be concentrating on in this end behavior of graphs. We're going to concentrate on that dominating term and the leading coefficient. All right. So now, since we talked about the dominating term, it says let a times x raised to the nth power be the dominating term of the polynomial. All right. So from this point, I'm going to kind of just break off to the one note for just a second. Okay. So we have end behavior of graphs. Can the end behavior of graphs is, believe it or not, it's a twofold deal. Okay, you're either going to have graphs that are going to look one way or another way. So the first thing is just keep in mind that we're concentrating on the dominating term, right? Which would be, and I'm just going to go back, this a sub n, a times x to the n power. It says where a is greater than 0. Wherever you see greater than 0, that simply means positive. N is your power. All right, so we're going to take a look at graphs that have a positive leading coefficient with an odd exponent. And this is the graph it takes. If your leading coefficient is negative, so whenever you see less than 0, that's simply negative, right? The mathematical term for negative. And if your power is odd, your graph looks another way. And then if we take a look at the two rightmost graphs, we have a is positive and n is even. And then our second setup, a is negative, right? The leading coefficient is negative, but the power is even. Okay, and this is the graph it forms. All right, so let's take a look at an example. Okay. Now, before we take a look at some examples and some more explanation, this is basically what we are going to attempt to do. We have 4 functions, right? We have an f of x, g of x, h of x, and k of x function. We're simply asked to match the graph with the function. Now, you can do this one or two ways. You can simply pop the graph in your calculator and match the calculator graph with the answer choice. Okay, or if a calculator is not available, here are the analytic methods. Okay, but in a nutshell, and if you're pressed for time on a test, I would simply graph it and match the graph to the answer choices. All right, but for some further explanation, we're going to talk about how we can just sort of look at a function and basically tell what equation it could possibly have. All right, so we're going to look at this in 2 setups. We have an even side and we have an odd side. So in this first setup, we have a is positive and n is even. So I'm going to just use a basic function. I'm going to use before I actually use a function, all right, if your leading coefficient is positive And if your exponent is even, right, your graph is going to rise to the left and is going to rise to the right. Okay. Now, if you're looking at this graph, you may notice that why is he putting these dots in the middle? Okay, and not just connecting a line. It's because if you're dealing with a function that has, let's say, a fourth power, right? Let's say if we're looking at y is equal to x to the fourth, that means that your graph can touch the x-axis up to 4 times, right? It may not touch 4 times, but it can't touch more than 4 times, right? If we have y is equal to x squared, right, that x squared means that the graph can touch the x-axis at only 2 points. All right, so to account for that, I'm sort of using these dotted lines. And also, if I go back quick and take a look at the model forms, you'll notice these dotted lines as well in the middle. Okay. All right, so here's the next setup for even. If a is less than 0, right, so that means the leading coefficient is negative, and n is still even, your graph is going to look like this. It's going to fall to the left and fall right. So let's take a look at some examples. All right. We'll take a look at this first example where we have a is greater than 0 and n is even. Here will be some examples. Y is equal to x squared. I'm going to bring up the calculator for a second. We're actually going to graph these as we go through. All right, so if I were to graph, I'm going to go into, first of all, I'm going to turn the calculator on. I'm going to go into y equals. I'm going to clear that out. I'm going to put in x squared and graph. And then just notice the end behavior of the graph. It rises to the left, it rises to the right. I can also put in x to the fourth power. So I'm going to go back to y equals. I'm going to put in x. I'm going to raise that to the fourth power and graph. And then notice the end behavior. It rises to the left, it rises to the right. I can also put in y equal x to the sixth power. Right? So for each one of these functions, the leading coefficient is positive. Right? So let's say this can even be 2x to the 6. Right? If I were to graph 2x to the 6, it should take on this general form. It should rise to the left and rise to the right. So I'm going to just go back to y equals. I'm going to put in 2x raised to the 6. Right? And notice that it rises to the left and it rises to the right. So the only thing we're concerned about is the end behavior. Now on the flip side, if your leading coefficient is negative, but your power is still even, your graph takes on the upside down U shape. So here's some examples. So y is equal to negative x squared, right? That would be an example. And we're going to graph that in just a second. y equal to negative x to the fourth. And we'll do another one. Y is equal to negative 6x to the 6. All right, so let's graph these and just take a look at the end behavior. All right, so I'm going to clear that out. I'm going to put in negative, so I'm going to use the negative x squared. And if we graph, notice that it forms an upside down U shape, right? It falls to the left and it falls to the right. I'm going to put in negative x raised to the fourth. We're going to graph that. Right? Notice that it also falls to the left and it falls to the right. And I'm going to put in negative x to the sixth power. I'm going to clear that out. Negative 6x raised to the sixth power. And notice that it falls to the left, falls to the right. All right, so now let's take a look at and I will take a look at odd functions. So if a is greater than 0, and if n, which is the power, is odd, then your graph is going to fall to the left and rise to the right. Right? So if your leading coefficient is positive, but your exponent is negative, right? That graph is going to fall to the left and rise to the right. If a is negative, so less than 0 means negative, and if n is odd, your graph will okay, that looked a little bit better. It will rise to the left and fall to the right. Okay. So let's take a look at an example or some examples. So we'll take a look at this first setup. Our leading coefficient is positive, but our power is odd, right? So we have x cubed. We also have x, right? Right, because x has a power of 1, 1 is odd, x to the fifth, so on and so forth, right? So I'm gonna just graph a couple of these. I'm gonna go to y equals, clear out a graph. I want to put in x cubed. Right, and notice that it falls to the left and it falls to the right. I mean, it falls to the left and it rises to the right. We can put in y equals x, right? And it falls to the left, rises to the right. He could also put in x to the fifth, and you'll see that it falls to the left and it rises to the right. And now for our last setup, we have the leading coefficient is negative, and we have n is odd. So some examples would be y is equal to negative x cubed. Y is equal to negative 4x to the fifth, so on and so forth. Right. So just to see the graphs, I'm going to go back to y equals. I'm going to clear out those functions. I'm going to put in negative x cubed. Right. So notice it rises to the left, falls to the right. I'm going to put in negative 4x raised to the fifth power, and notice that it should rise to the left and fall to the right as well. The difference is how many times it can actually hit the x-axis. All right, so let's take a look at All right, so let's take a look at the questions. Okay, here we're going to match the graph with its functions. I'm going to actually pause the video here. I'll give you 5 minutes or so to kind of work out the solutions, and we'll return and take a look at the solution together. All right, let's take a look at the solution. All right, so if we take a look at the f of x equation, now the only thing we're concentrating on is the, and I can't actually write on this. Only thing we're concentrating on is that dominating term, right? So we're looking for the variable with the largest exponent. So for f of x is x to the fourth, right? So that exponent is even. So it's either going to take a U shape or an upside down U. Next, I'm going to look at the coefficient. Since the coefficient is positive, this should take on C, right? It should rise to the left. It should rise to the right. If I take a look at g of x, notice that its dominating term is the 6th degree term, right? Which means that it has an even power. So it's either going to form a U shape, or it's going to either rise to the left, rise to the right, or fall to the left, fall to the right. We look at the leading coefficient, it's negative, so this would take A, right? The form of A. It should fall to the left and to the right. If we take a look at the h of x equation, notice that the h of x equation has a cube as its dominating term, right, which is an odd power. The leading coefficient is positive, so this would form that S shape, right? It would fall to the left and rise to the right. So the h of x graph would be B. And then lastly, we have the k of x graph. Now, by default, it's going to be D. But if we take a look at the dominating term, we notice that it's a 7th degree term, which is odd. Its leading coefficient is negative, right? So it's going to take on that reverse S shape. So it should rise to the left and fall to the right. All right, so that is the end behavior of graphs. Now, as far as the module 4 is concerned, there is one more topic that we are going to discuss, and I'll kind of talk about the exam shortly. But I'm going to kind of set it up for today. We're actually going to get into it Monday, and it's something called asymptotes. Now, I'm going to go back to our home page for a second. I'm going to go in this Documents tab, and I have posted another document. All right, I posted this asymptote cheat sheet document, and this is what we're going to be using when we meet again. So I'm going to click on that. And this asymptote cheat sheet, it basically gives you some shortcuts for finding what are called asymptotes. All right. We can have what are called vertical asymptotes. We can have what are called horizontal asymptotes, and something that is called an oblique asymptote. Now, before we end this session today, I'm just going to explain what an asymptote is. When we meet again, we'll actually go through this cheat sheet and we'll actually find these asymptotes. All right, but just to set up a general working definition of an asymptote, okay, an asymptote is an imaginary line so notice it's a line, so it has to be the straight line. An asymptote is an imaginary line that your graph gets close to but will never touch. And I'm going to underline that word never, because there are some asymptotes that do touch but then they kind of bounce back, and in the long run, they never touch. But for our working definition, the asymptote is an imaginary line that your graph gets closer and closer and close to, but it'll never actually ever touch it. All right. So here's some examples. This would be an example of a horizontal asymptote. I'm going to try to draw this to the best of my ability on this computer screen. So let's say we have an X and a Y chart, right? Or X and a Y axis system. And let's just say this is our graph, and it does something like this. All right. So notice that this would have what's called a horizontal asymptote. If I were to take and dot the x-axis, the asymptote, this would be a horizontal. Okay. The horizontal asymptote is a line your graph gets close to and never ever touches. The horizontal asymptotes are, in a nutshell, basic linear equations. So when they ask you for an asymptote, they're actually asking you for an equation. The equation for the horizontal asymptote here would be y equal to 0, right? Because that little imaginary dotted line would give me the equation y equal to 0. Notice that our graph gets closer and closer and closer to that line, but never actually touches the line, right? And that's called a horizontal asymptote. We also have, I guess before I go any further, I'm just going to do a Google search and put in horizontal asymptote. All right, so here's some good pictures. This has it all in it. All right, we'll just take a look at this one. This says identify horizontal asymptotes, but this actually has horizontal and vertical. We'll take a look at this horizontal and notice this green dotted line. That would serve as a horizontal asymptote because notice that our graph, it gets closer and closer to that line, but never actually touches the graph, or it never actually touches the line. And also on this side, right, it gets closer and closer to this horizontal line, right, which has the equation y equal to 3. So that would be considered the horizontal asymptote. Right, a vertical asymptote is a vertical line that your graph will touch without actually coming close to. So I'm going to draw this one like this. All right. All right, so let's say this is the graph, and this would serve as the vertical asymptote, right? This would be that vertical line that your graph would come close to but never actually touch. And it would be in the form of, I'm just going to kind of put something here. This would be x is equal to -3, right? That would serve as the horizontal, the vertical asymptote. So when you're asked to find these asymptotes, you must list the asymptote in the form of an equation. And next we're going to look at something called, it's called an oblique asymptote, or sometimes you may see it in textbooks as a slant asymptote. And what it is it's a slanted line or an oblique line that your graph will come close to but never actually touch. Right, so I'm just going to do another search. And this time I'm going to put in oblique asymptote. Okay, and this would be an example of an oblique asymptote. Right, so notice for this graph, it looks like it actually has a vertical asymptote and an oblique asymptote. Okay, but more importantly, the oblique asymptote or the slant asymptote is that slanted line. Right, so notice how this graph comes close to the slanted line, but never actually touches the slanted line. Okay, so those are the three types of asymptotes. And what we're going to do in the next section, or in the next class session, we're going to find the equations for these asymptotes, and we're going to rely on this, what I call cheat sheet. All right, so at this time, I'm going to stop the recording.